Hello, and thank you all for coming. I'm Alexander Leacano,
I'm Elizabeth Lopez.
And I'm Daniel DiStefano.
and we're here to talk to you about the KE PowerShoe. On average in the US alone, over 2 billion pairs of shoes are sold per year, and the average person walks between 13 and 1,500 miles. Now, we use that on our average day. Why can't we take that energy we put forth to just go throughout and not use that to charge our phone, our iPads, our tablets, anything?
So we made the KE PowerShoe, which is a shoe that creates energy by walking with kinetic energy. And there's one battery per shoe. As you walk, it creates energy, which goes into the batteries. And in total, when you remove them and put them in the battery box, it equals 2,100 milliamps, which is the average amount for a portable charger.
And our specific criteria, we had to break it down between safety, how comfortable it was. It had to be lightweight, it had to produce around 4 millivolts, it had to be waterproof, have easy accessibility, have good power storage, and be reliable. We rated everything on a scale of 5 to 1, 5 being the best, 1 being the worst. And throughout this test, we found that the wedge piston with a battery was the best option for us. And we defined safety as it does not catch on fire, it does not shock the user, and then how comfortable it was, it does not affect the walking motion, it's not painful to walk in or stand in. Lightweight, we wanted the whole system to be under 1 pound, and the power production, it has to produce more than 4 millivolts, it has to be waterproof, or the whole mechanism be inside a sealed container to where it is waterproof. Accessibility, the batteries have to be easily accessible. Repairs have to be, if they have to be made, they need to be has to be easy to be done. And power storage has to store up to or more than 2,100 milliamps. Reliability has to be durable, it won't crush under your body weight, and we want it to last around or more than a year.
These are different drawings from the different stages before we started designing. These are the hand-drawn isometrics.
And so, finally, we just went with thicker, solid walls and minimal overhang. The only reason we had these is so it guides the incline on a horizontal motion, keeping everything nice and contained.
This shows our invention all set up. We added 3 springs from a pen right here. And then when we were making the incline, we embedded metal rods, and then we used the magnet's natural properties to hold it together.
Here we have a picture of the whole mechanism put together. The lid is being held on by screws, but in our final product, we would have the top melted into place so it created a more waterproof seal. And this is a bottom and top view, just emphasizing how the screws went all the way through to hold the lid on. And you can see the wires can snugly fit around the edge without being harmed in any way.
Okay, so this shows the magnet right here when force is not applied, like so when in between steps, and then this shows when you'd be taking a step that the magnet is pushed through the coils. This is a stress test to show that the weight is dispersed where we want on the incline.
Here's the full exploded view and adventure of all the pieces in its final assembly. This just shows how snugly they can fit, and they all have their designated area. The magnet within the coil spacer, the incline under the rails, and the pressure plate in its hole. Here we have the hollowed out view of the shoe. Now, in a final product, we would have to raise the heel and the rubber just to keep it safe and comfortable.
Okay, this is the electronic part of the circuit that goes inside of the shoe. And this is where the input wires would be for the generator. And then this shows where the battery would be. This is basically the same circuit design for the circuit that goes inside of our battery box. This shows where our batteries would go. And then this is where the USB would be, so you could charge a smartphone. You could charge an Apple phone, Android phone. It's really universal. This shows why we use this chart to help us figure out why we chose AA batteries. And we chose AA batteries because they are less expensive and they are more common. But we also were considering going with C batteries. We found out that our product produced 3.8 volts, which is a pretty good amount of voltage. And this is our battery box. So once the batteries are charged, you take them out and you put them right here in this battery holder. And then right here is where you'd plug in your phone for the USB.
The final steps we'd have to take in developing this product is we'd have to make the case out of a stronger material, maybe a aluminum or maybe a carbon fiber. Customizing and printing out specific circuit boards so everything can fit where it needs to, and we don't have to deal with solder bridges and other messy different processes. We'd have to make it more efficient so it can charge faster in fewer steps, so maybe it doesn't take an entire day or 3/4 of your day. Maybe it takes half or even less than that. We'd have to put a patent on it just so we can have this to ourselves and distribute to where we think it needs to go. Specifically, me and Dan learned designing the boxes and the different parts that the forces can be applied in a lot of different ways than standard flat planes. That's why we went with the rounded edge. Second thing is there's a lot of force on a small area, and dispersing that so it doesn't collapse upon itself is rather difficult.
One of the things I kind of learned was never overlook like the little things, like having the support pegs on this coil spacer. You never would realize how much the coils would move or how easily they get crushed and how much it could hurt you in the end if you don't realize that it happens. So kind of looking at all the little small things, making sure everything is concise and everything works perfectly, kind of emphasize on that and how important it is and how much you need to watch out for it.